Hello guys, this is Paul McWhorter with TopTechBoy.com, and we are here today with lesson number 26 in our incredible tutorial series where you are learning about inertial measurement systems. What I'm going to need you to do today is I'm going to need you to pour yourself a nice big mug of iced coffee. And I am going to need you to also pour yourself some hot coffee because this is going to be a long lesson. It's a long lesson, but it's an important lesson because what we're going to learn today is we're going to learn about PID controllers. We're going to learn the theory behind PID control systems. And we're going to demonstrate that PID control system on the platform of our self-leveling Arduino B&O 055 system. And so we have a B&O 055 9-axis inertial measurement system, sensor. We have an Arduino Nano. We have a power supply, and then we have two servos. And the idea is you measure the position with the sensor, and then you apply a correction signal to these servos so that this platform will self-level. Now we have done quite a bit of work on this in 26 lessons, and we are sort of to the point now that we have something with a very simple control system that will actually work. We basically have a self-leveling platform, and so I can kind of show this. It takes a second to find its level. Let me reset it. Okay, so you can see that if I tilt it towards me or towards you, it self-corrects. Pitch, it self-corrects. And so using the sensor in a very simple control system, no matter where I move my hand, the system will come back and level itself. Well, that looks really, really cool. But the problem is it's a very, very simple control system. The nice thing about the simple control system is it's easy to implement. The problem is when we actually go in and look at it, it doesn't really perform very well. So what we're going to learn today is we're going to learn about PID controllers, how they work, and then we're going to program it into this system and show you how much better the system works when you have a true PID control system. So I think at this point we are going to jump over here and we are going to start talking about the theory of PID controllers. And the first thing that you have to understand when you're talking about control theory is you have to understand the concept of error. Okay, whatever it is that you're trying to control, whether it's temperature, speed, RPM, angle, whatever you're trying to control, you got to think there's a place that I want to be, there's a place that I am, and between those two there is an error. And so you really do all the theory around that error. But the theory works for whatever control system that you're trying to do. For us, what is the parameter of interest? The parameter of interest is angle. And the target is 0 degrees. If I tilt it like this, I have put it at 45 degrees. The difference between where I am and where I want to be, that's 45 degrees. That's my error. And the idea of a control system is to look at that error and then be smart in the way that we eliminate the error. And so let's look here and let's just kind of review like what would be the simplest way that we could control the error of this system. And I believe this is what we actually did in lesson number 24. So let me draw it out and let's think about this. This is the target, and I'm going to introduce a 45-degree error. Let's just say I'm going to introduce a 10-degree error so it sort of matches my drawing here. So let's make sure I have the right pen. So I'm coming here, I'm flat, so I have an error of 0, and then very quickly I tilt it to 10 degrees, and so now I have an error of 10 degrees. Now the simplest control system possible is called constant correction. Okay, and that means the correction signal is the same whether you have a big error or a small error. And so let's say that our constant correction factor is 1 degree. So if I'm off by 50 degrees, the correction will be 1 degree per cycle. Or if I'm off 3 degrees. The correction is 1 per cycle. So the way that would work is I introduce a 10-degree error, and then the first time through the loop, I take out 1 degree. The next time through, I take out another degree. I look, I'm still too big. I take out a degree. Still too big, take out a degree. Each time through, I say, is my error positive? Yes, take out a degree. Yes, take out a degree. Take out a degree. Take out a degree. And so forth until I come and I had this error. I drove the error to 0 1 degree at a time. Now, why would you want to do a control system like this? Because it is very simple, right? It is as simple as possible. If I'm too large, I make it smaller, 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 smaller. If I'm too small, I make it larger, 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 larger. And that correction factor is a fixed amount. For this case, it is 1 degree. So one good thing about a constant correction control system is it's very simple. Another one is it is very stable. Okay, if you look at this, I gradually correct until I get to my target, and then I stop correcting. It tends to be very stable. Well, why don't we just do everything with a constant correction algorithm? The problem is it is slow. Okay, because even if I'm 50 degrees off, I just correct 1 degree at a time, and that turns out to be very slow. And so then that led to what we did in lesson number 25, and that was, let's be a little bit smarter about what we do, and let's make the correction factor, the correction signal, to not just be a constant, but let's have it be proportional to the error. So let's just say that what we would like to do is we would like the correction signal to try to correct out half the error each cycle. So let's see how that would work. Well, I come up here, I have 10-degree error. Well, I'm going to try on the first cycle to take out 5 degrees, and then on the next cycle I'm going to take out half of that, 2.5 degrees, 1, and then very quickly we eliminate the error. Okay, we eliminate the error because we're doing it. That is terrible. Let's see if I can get rid of that. Okay, let's see if I can draw that better. I did a little loop-de-loop there. Okay, let's see if I can draw this smoother. Okay. So you see, it's about twice as fast using a proportional control system. As you get closer to the target, you have smaller and smaller corrections. So that works pretty good. And so in this case, what we are doing is we are doing proportional control. Proportional. And let me go ahead and show you PID. Okay, PID. The thing for you to see is what we did last week and what I just drew up here. That is the P in PID. It's proportional. And that means that your correctional signal is some constant K1 times the error. And that K1, like, I think we used about 0.3 or 0.5 last time, so each time we were trying to take out about half the error. Well, that worked pretty good. So you might ask yourself, why don't we just make everything proportional control? Well, the problem is, if you look at it, you would really like to go a little bit faster. And if you wanted to go a little bit faster, what if we said, instead of taking out half the error each time, what if we took out 80% of the error each time? Okay, we're going to try to take out 80% of the error each time. So we come up here, we have an error of 10 degrees, so we're going to take out 8 degrees of error. But look at that. If you think that you sling this thing that far in one step, you're building up a lot of momentum and you're almost to 0. And what's going to happen? You're going to overshoot, and now you've got a negative error, and then you overshoot here and you overshoot, and this thing begins to ring. And so if you're using proportional control and you're trying to make it go fast, what happens is you overshoot, 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 And even though you're moving faster and you're taking out more error, you end up introducing this ringing, and it's actually slower than if you had just used a proportionality constant that was less. And if you try to apply too much proportional control, it'll actually become unstable. You'll lose control and the thing will just fly all over the place. And so the problem with a proportional control only is that you end up what would I say? You end up with a fundamental trade-off between speed and stability. And you can make it stable, but it'll be slow. You can make it fast, but it will be unstable. So what you want to do is you want to get a little bit more clever in how you do this thing. So I'm trying to get rid of some of these. Let me see if I can just, maybe I can erase these. Let's see, give me just a second. I don't want to erase everything. Okay. Erase these data points. I want to leave that first curve. That's why I'm doing it this way. Okay. Actually, I think I'm going to take out the P curve too. All right. So now let's think about how we could be a little bit smarter about this. All right. So we are here at 0 degrees. We introduce a 10-degree error. Well, chances are you would make a measurement, like let's say right here, so you see that you're good. As you start tilting, all of a sudden you have like a 3.5-degree error, and then boom, you have a 10-degree error. Well, let's think about how you would think about it as a person versus how the proportional control system thinks about it. The proportional control system looks at it and says, well, I've got an error of about 4 degrees. I'll apply a correction of 1 degree. You see, it's thinking 4 degrees, it's not that much. Small error, I'll apply a small correction. Okay. And what is the problem with that? Well, as a person, you see, I was at 0 degrees and all of a sudden I'm at 4 degrees. I'm losing control. I need to sort of panic and get it back under control. Like if you think of this was a car and you're going this way, it's like you're going to spin out of control. So what really you see intuitively as a person, one of the things that matters is it's not just how large the error was, but it's how quickly that error occurred. It's the rate of change of the error. And if you think about math, what is rate of change? Rate of change is slope, okay? And so you want part of your correction signal to not just be based on the magnitude of the error, but how quickly that error is getting there. So you kind of want a nice stable correction that's just based on the error, but then you want part of your correction to kind of be a panic factor that panics not on the magnitude of the error, but how quickly the error changed. And so we want a correction term that is going to be proportional to slope. Now, from your math class, what is slope? Slope is y2 minus y1 over x2 minus x1. Well, for our case, what is y? It's error. So for us, the slope would be error 2 minus error 1 over, what is our x-axis? Our x-axis is time, so our denominator would be time 2 minus time 1. Okay, that is slope in terms of algebra. But if you think in terms of calculus, the slope is the derivative. And kind of putting this more in calculus terms, we would say E2 minus E1 is what? That's delta E, the change in the error over what? Delta T. Okay, and that is more like the calculus derivative. So in a PID controller, You want one part of the correction signal to be related to P, and we did that here. And then you want another part that is proportional to D, the derivative or the slope. So you have proportional control, you have derivative control, and you can think of that, if you're not familiar with calculus, you can think of that in terms of slope. And so you want that term to be K2, a second proportionality constant, times what? The change in the error over change in time. So if we have a fastly changing error signal, we respond quickly with this derivative term. Okay, so now what that would do is, when we get here, this would not just have a signal proportional to the error, it would have a signal proportional to the slope, and that would kick in quickly to turn this thing around and bring it back to 0. Okay, so we start our correction quicker because we see a fast changing signal, and when we add derivative control to proportional control, it really works very well. But let me show you something else about how we avoid that swinging past where we want. Well, once we turn it around and come down, and we start coming down, now the slope is not positive, now the slope is negative. So at that point, this derivative term is not speeding you up towards 0. It's backing off. It's not adding to the proportional signal. It's subtracting from it. And what that allows you to do is it allows you to begin to slow down and come into a nice smooth landing. So when you're getting away from where you want to be, you're piling on correction, and as you begin to come to your target, you're backing off. And so both on your way up and on your way down, this derivative signal is adding to the stability. It's making you begin to correct quicker and then backing off so you come in for a smooth landing. Man, this is so important, I feel like that I need to repeat it, okay? When I go from here to here, okay, I'm moving away from my target, so I'm going to respond with a signal that's proportional to the error, and also I'm going to add to that a derivative term. The slope is positive, so I'm adding more correction than I normally would. When I turn around and start coming down, now the slope is negative, so I'm beginning to back off of that proportional signal so that I can come in for a smooth landing. And so that is what you can do when you combine proportional control with derivative control. Well, what about this I term? That is, I guess I would describe it this way, that let's say that you ended up down here, that you came down and you ended up with a little error like this, okay? Why would you end up with a steady state constant error like that? Well, let's think about our control system. When we end up with a constant error, does the derivative term do anything? No, the slope is 0, it's not changing, so this correction term would be 0. And then for proportional, yes, there's an error, but I'm only feeding back a small part of that error, and so I can kind of just get stuck here at this small steady state error. And so what we want to do is we want to add in a third control signal, and that third control signal is I, or integral, okay? And integral, again, is a calculus term, but if you think in terms of algebra, it is a correction term proportional to area. And it is the area between the error curve and the target value, the 0 value. And so kind of think of it this way. The derivative term is a fast-acting panic term. The integral term is a slow-acting term to take those long-term errors out. And the way you can see it is at this point right here, what is the area? Well, it would be this shaded region here. That's real small. So would you get much of an integral correction? No. But if you come to the next data point, all of a sudden now what is the error? the area? Well, it's bigger because now I have 2 chunks of time where there was 1. And then after 3, it gets even bigger. So area is getting bigger and bigger and bigger. And so if you have something proportional to that area over time, it will see this integrated area and it will begin to apply a signal proportional to that to bring the area error to 0. And so this would be some K3, and that K3 is going to be multiplied by the area error. Okay, now what is the area error? Well, you see each time the area is getting larger. So what is that area term? Well, the area is going to be equal to the old area, okay, what the area was before, your old area, plus your new area. Well, what is your new area? Well, it's width times height. What is the width? Remember, it's delta t. What is the height? The height is error. So the overall area error is area plus width times height. Or I'll say height times width. Error times delta t. Okay, so this is a slow moving signal that we're tracking the overall error area over time, and we're slowly driving that to 0. Okay, so this term would be K3 times the area plus the new little slice, which would be the error times delta t. Okay, now what is our overall correction factor that we're going to put on this thing? Our overall correction is going to be equal to the proportional correction, which is some constant times the error. Okay, and this is the term that we used in lesson 25. Okay, but now to be able to have it be faster, more responsive, more snappier, and more stable as we're coming to our target, we're going to add a second proportionality constant, K2, but that is going to be related to the derivative of the curve, or you could think of it as the slope of the curve, and that is delta E over delta T. And then we're going to have some K3 times the integrated area, which is whatever area you had before plus error, that's the height, times the width, delta t. Okay, so do you see what this is? We're going to have a correction term each time through the loop that has 3 components. One component of the correction is related and proportional to the error itself. The second term is proportional to how quickly the error is changing. It helps you correct faster on the front end and then come in smoother on the back end. It helps you in the right direction both ways. And then finally, to get rid of that little remnant drift or slow moving error that you end up with after applying P and D, we have the I, the integral correction. And so now what we need to do is we need to go in and start building this into our code so that our correction on this self-leveling platform has 3 different parameters. How does that sound? Okay, so I hope this makes sense. You might need to go back and watch this twice. Okay, you might need to go back and watch this twice. But what I am going to do now is I will need you to go out and get yourself a fresh new Arduino IDE. And let's make sure you can see that. Okay. And then where we're going to start is we're going to start where we left off. We are going to start where we left off in lesson number 25. And so I need you to go to the most excellent www.toptechboy.com. I'm going to need to go to a different view here. I think this will be a better view. Is that going to work? Yeah. So you're going to go to www.toptechboy.com, and I need to get this to make sure that you can see it. And I'm sorry this top camera isn't really pointing at anything, but I'm going to point it at the platform when we actually start. I'm going to point it at the platform when we actually start doing the correction. So right now you're just looking at some junk on my desk, but you need to go to www.toptechboy.com. You need to go to non-access IMU lesson number 25. You can get there with the little search icon, and then you can come down and you see the code. You can click these two little pages. That selects all the code. You can do a Control C and then come to your Arduino and do a Control V. And now I need to make sure that you can see this all the way. So that looks pretty good. Okay. I think that's going to work. So this is where we left off in lesson number 25, and this is our proportional control system. So let's see if we can go ahead and download that, and just let's sort of look and see how this thing behaves with our proportional control. So I got to give it a second to download. That looks like it downloaded. Now I will come and I will turn it on. Let's see if I can give you a nice shot of this. Okay, so what I'm going to do is I'm going to roll it towards you, and you can see it corrects. I'm going to pitch down, it corrects. I'm going to pitch up, it corrects. I'm going to roll it towards you, so you see however I move this, it corrects. Well, that looks pretty good, right? That looks like it's working until we go to our actual plotting of the data. And what I'm plotting here is the orange is the error in pitch and the purple is the error in roll. And so let's see if we can turn this thing on. Okay. And that seems to be working. What I'm going to do, I'm going to give about a 45-degree pitch or 45-degree roll your direction. Okay. And what you see is, what is the problem? Let me see if I can stop this and kind of look at this. What is the problem with this proportional control? Yes, it brings the error to 0, but look at this. This is what I was talking about. I rolled it towards you about 45 degrees, but when you had like a 5-10 degree error, it's thinking, I'll give it 2 degrees of correction. Well, I'm on my way to 45 degrees. I got to have a bigger correction than that. And by the time it starts correcting, it's all the way up to 45 degrees. And now it's correcting great big, and it's slinging it back quickly, and it comes in too fast, and it overshoots by 20 degrees. And so you see you end up with this overshooting and this ringing in the data. So we need a better control system so that we can operate quickly and stably. And hopefully this data kind of shows you what our problem is and what we are trying to do. Okay, so let's think about this. What we need is, we need in the code, like we already in the code, we sort of already in the code have this K1 times the error factor. And so we're going to need to add these other two components. All right. Well, in order to do that, we're going to need a lot more variables, right? We're going to need a variable for slope. We're going to need a variable for area. To get the variable for slope, we're going to need to have a change in error and a change in time. So there's a lot more variables that we're going to have to use. And so let's just jump in and start. Okay, we've got, let's see here, we've got where we left off in lesson number 25 here. And what we're going to need to do now is we're going to need to go in, and the first thing we're going to do is we're going to set up our new variables at the top of the code. And I'm going to explain these variables a lot, and that way when we get down to programming them, it's going to kind of make sense, because I really explain them in the setup. So we're going to have to define new variables. So let's see here. We come in and we load our libraries in the code. We create our servo elements. We define our quaternions, okay? And then after the quaternion definition, this is really where we want to come in and kind of start putting in our new variables. And again, we're trying to program those equations, and that is creepy having that thing point at me. So I'm going to turn this back to nothing. Okay, so we've defined our quaternions. Now we need to begin to put in our new variables. And if you think of our equation here, you can see that we have three proportionality constants, K1, K2, and K3. And so we probably should go ahead and define those and then start putting in our other variables. And so we're going to have our proportionality constant K1. That is going to be a float, and K1. We know that just from our earlier work that a value of about 0.5 would probably be right. That's saying that each time through we want to take out half the error. So our proportionality constant is going to be 0.5. Now we're also going to have a second one, K2, and this is going to be associated with the derivative, and that needs to be a lot bigger, okay? And it has to do with the fact that we're measuring time in milliseconds and we're dividing by milliseconds, and so this is going to be a lot bigger. This is going to be like 250, okay? So we're going to have a large signal of correction, or a large proportionality constant for that derivative term. And then finally we're going to need our third one, float K3, and this is that integral term. So this is the proportionality constant for the integral term, and we're going to make that 0.001. All right. Now, why is K2 really big and K3 really small? Well, because I'm operating in milliseconds. In a short amount of time, you have a lot of milliseconds, so milliseconds is going to be a large number. And in K2, I'm dividing by delta t, so I'm dividing by a large number, so the proportionality constant needs to be big to offset that. And kind of oppositely, the integral term is multiplied by delta t, it's multiplied by delta t, which makes it a big number, so I need a small proportionality constant. And so 0.5, 250, and 0.001, really, they're all kind of putting more or less equal weight between the three terms if you think about the fact that delta t is measured in milliseconds. Okay, I hope that makes sense. But I got those two proportionality constants. I think what I'm going to do is I'm going to make this probably 0.5. I'm going to make this probably like 70, a little bit smaller, and then that 0.001. All right, so now I have my proportionality constants. Now if you think of that equation over here, you will remember that now I've got this very important concept of delta t. That is, how much time has elapsed since the last measurement. Okay, it's like the old time, it's the new time minus the old time. That's the change in time. It's T2 minus T1. The old time, the new time minus the old time, that's delta t. So I need to get kind of this timing business in there. So I'm going to have some new variables. I'm going to have milliseconds old. That's like where the clock was last time through the loop. Okay. And then I'm going to need milli new. That's where the clock is this time. So last time through the clock was at milli old. This loop through, I'm at milli new. And then what would I have? Well, I would have dt for delta t. That's the change in time. Now I'm not putting equations in now. I'm just declaring my variables, but I'm telling you what I'm going to do when I get down in the loop. dt is going to be the new milliseconds minus the old milliseconds, and that's going to be dt. Now if you think slope is delta e over delta t, I've got the denominator now of the slope. So that's kind of neat, or at least I've got the variable set up for it. And now what I'm going to need is I am going to need to define some variables associated with our control. Now before we were doing proportional control, so we already have this concept of a target roll, and then we have an actual roll, and then the difference between the target and the actual is the error. And then we've got some value that we send, some signal that we send to the servos. And so those were the variables that we needed to do proportional control. But now we're not doing proportional control. We are doing proportional differential, and integral control, so we need more values. We need more variables. And so you've got this idea of roll error, and I'm going to go ahead and I'm going to put roll error. I'm going to go ahead and I'm going to put roll error at 0, just so when it turns on it doesn't start flying around. I'm going to kind of tell it you're okay where you are, so it gives the loop a chance to start working. So I've got roll error is 0, but now if you think our delta E, our change in error, is the error minus the old error. That means I need 2 roll errors. I need roll error, that's what the error is this time, and roll error old. That's what the roll error was last time. Okay, so if I'm going to take a difference in error, I've got to have 2 error values, the one this time through the loop, the one last time through the loop. Does that make sense? Okay. Well, what did I want? I want change in error. Okay, you know, the delta E, change in error. And so that would be roll error change. Okay, when I program it, what's roll error change going to be? Well, it's going to be roll error, the error this time, minus roll error old, the error last time. Okay, and so then I'm going to need float. I'm going to need roll error slope. Okay, and what is the roll error slope going to be? Well, the roll error slope is going to be the change in the error over the change in time. I just did change in error, I did change in time, I divide those two, and I'll be able to get this term. Okay, so I have roll error change, and then roll error slope is going to be roll error change divided by dt. Just making sure I've got all the variables I need to do the calculation later. Then also remember, those are kind of the derivative terms. I better not say sol error, I better say roll error. Okay, now what else am I going to need? I also have this area term, okay, and that would be like the roll error area. Okay, and that is going to be, if we look over here, that is going to be, like I showed you down here, over time, this area between the error and the x-axis. And so I need a variable to keep track of that. So that is an important variable. All right, roll error area. And I think I'm going to set that to 0 too, just so it, you know, kind of starts without trying to do a correction. You got to give the loop a chance to actually start working. And I'm going to set the roll error slope also to 0. And this means the first time through the loop, it's going to give the sensor a chance to start working before it starts correcting, and it kind of keeps it from running away from you when the loop is just getting cranked up. All right, so we're going to need to do those same things with pitch. And so we've got pitch target, pitch actual, pitch error. We're going to go ahead and we're going to set that to 0. And now we got to start putting in our new variables. All right, so I'm going to need float, and I'm going to need pitch error old. That's what the pitch error was last time through the loop. And then I'm going to need float pitch error change. Okay, and then I'm going to need float pitch error slope. I'm going to set that to 0. I'm going to go ahead and set that to 0. And then I'm going to need float. I'm going to need pitch error area. Okay, and I'm going to go ahead and set that to 0 equals 0. And then my initial servo value for both of them are set to 90. So that's just saying set it at 90 degrees, 90 degrees. That should roughly set it to the flat position. Okay, does that make sense? That looks pretty good. That looks pretty good. So now I've got the variables that I need in order to go in and start programming up that equation that we're trying for. And I'm wondering if I can kind of try to show you that equation with my camera. Give you something a little bit more useful to look at. This is kind of hard to balance, but let's see if I can get it. Hey, I think that you can kind of see what we're going to start trying to build now is we're going to start trying to build this correction factor. It's going to be our K1 times our error plus our K2 times our slope plus our K3 times our area. All right. And we are going to start trying to program this thing up. And so I'll leave that equation so you can kind of look at it as we are trying to do this. Okay. So I need to come down and kind of see what different things we have. We're modifying this code from before, so we're defining our sensor. We're loading our sensor libraries. We're turning on the serial monitor. We're turning on our sensor. We're telling. We're setting up the servos, and then we are putting our servos to 90 and 90, so it kind of, the servos will start in kind of a nice flat position, so it'll be kind of the position from which we then start doing our control. So just trying to get it where it'll start up nice and easy. Okay, now that is the void setup. Now there's kind of a little quirky thing we have to do in the void setup, and what that is remember that our change in time is going to be our new time minus our old time. But the first time through the loop, we don't have an old time because it's the first time through. So we need to do that first time measurement in the void setup right before we go in the void loop. And so here we're going to say milli new is equal to millis. And that will give us a value to use the first time through the loop so the program doesn't crash. Okay, now we're going to get down into our loop, and let's see what we do here in the loop. We pull the data off of the IMU, we get the quaternion vector from the IMU, and then we put those quaternions in Q0, Q1, Q2, Q3. So that's the data from the sensor. Then from our quaternions, we calculate roll actual and pitch actual. Okay. That's what we want. We want roll actual to match roll target. We want pitch actual to match pitch target. But to do the control, we have to have a measured value. And we have to measure that value every time through the loop. So here at this point, we have actually where our roll is and actually where our pitch is. Okay. And that returns the values in radians, and we want to work in degrees, so we convert those to 2 degrees. All right. And now this was our old control here. We did it with these if statements. So I'm just going to take this out, starting with the second if statement up to this roll error and roll target, roll error and pitch error. I'm going to take all that out, and now we're going to start building our control algorithm from scratch. The good thing is we have all the things we need, and we can start doing it. Okay, the first thing that we need to figure out is we need to figure out, like we're going to figure out slope. Slope is delta E over delta T, dE over dt. Well, I need to figure out what that dt is. Well, I need to put milli old is equal to milli new. Now that sounds strange, but what you got to think about, last time through the loop, that milli new, it's no longer new. It's got to be put in milli old. Last time through the loop, I had a milli new. This time through, that milli new is no longer milli new. It's now the old value. So I've got to take my milli new, and I've got to put it over in milli old. Okay, now what do I need? I need a new milli new. Okay, and that's going to be millis. So I just go out and read the clock. Okay, so my new value gets the clock. Okay, so now I've got a new value and I got an old value. Well, what do I want to do? Well, I want to subtract the two. Okay, I want to subtract the two. So dt, the change, the delta in time is going to be milli new, what I just measured, minus milli old. Okay, what's the good news? The good news is I now have this delta t that I need. I now have that delta t. Okay, so you see I'm trying to build this formula. I've got the delta t down here. I use delta t here, I use delta t there. I've got it now. That is really very good. That is what I needed. Okay, so let's bring this back up. Hopefully that makes sense. So I've taken care of my dt. All right. Now I've got to take care of the error 2 minus error 1. Well, what you've got to see is we are doing two totally separate control systems. One is controlling roll and one is controlling pitch. So I've got to do everything twice. One for controlling roll and one for controlling pitch. I'll do the roll control first. Well, what is the first thing that I need? Okay, well, I need two roll values. I need the old roll value and the new roll value. Okay, so what I'm going to say is I'm going to say last time through the loop I had a roll error. Okay, I need to save that now. That becomes what? Roll error old, because roll error, it's no longer the fresh one, it's the old one. So roll error old is going to be equal to what? Roll error. All right. And I think I might need to make sure that roll error has a value up here so it doesn't crash the first time through. Pitch error, roll error. Okay. I just want to make sure the first time through the loop there are actually numbers in there, and it does appear that there are. Okay, so I have roll error old is equal to roll error, so that roll error, I put it in old. Well, now what I need is I need to get the present roll error, and what is that going to be equal to? Well, that's going to be equal to the roll target where I want to be minus the roll actual. All right, and how did I get roll actual? Well, I measured it up here, right? I measured it. So I take that measured value and I subtract it from roll target, and that is roll error. Well, now what do I have? I have two roll errors. I have the one last time through the loop and the one this time through the loop. So what do I need? I need to find roll error change. How much did the roll error change between last time and this time, between the last time through the loop and this time through the loop? Well, that is pretty easy, right? It's the roll error this time minus roll error old. Okay, so that would be the change. The present value minus the old value is the change value. So now I have roll error change. But it's not really the roll error change that I want. What is it? It's the slope. It's the roll error slope. Roll error slope. And that's equal to what? Let me just see if I can let you look at it here. Remind you, right? The slope is the change in the error divided by the change in time. Well, I just calculated the change in error, roll error change. So roll error slope is what? Roll error change divided by what? Somebody tell me. Divided by what? dt. And I've got those values. So now, I guess I could show you over here. So now, what would be something good and suitable to point with? Now I not only have my error term, which we're calling roll error, I've got my K1, that's good. I got roll error, I got K1. What I also have is I have K2, and I have the change in roll error divided by the change in time. So I've got this whole term and I've got this whole term. That is pretty slick. So what do I need to work on now? I do believe I need to work on that third term. Okay, I need to work on that third term, that I term. I've done P, I've done D, I need to do I. And what is that going to be? Well, I need the roll error area, and that is going to be roll error area plus roll error times dt. So every time through, I take that little bit of error area and I add it to the area, add it to the area. So over time, that small area is going to get bigger and bigger and bigger because you just keep adding to it, and then that will force that small error to 0. All right, so roll error times dt. So I have roll error area is roll error area, what it was before, plus the error times dt. Okay, I think 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. That looks good. Now remember, we're doing 2 control systems, so I'm going to need to do that same thing with pitch. And I think the easiest way to do that, I copied and pasted, and I'm going to put pitch here. And now I'm going to copy pitch, and then I'm just going to come in and I'm going to paste. Everywhere I have roll, I'm going to paste pitch. And the bad thing about this is everywhere that I had an error, I just copied and pasted the error. But we will figure it out later when we run it. You got to make sure you change all of these, because if you have a roll parameter floating around in your pitch calculation, it's not going to be pretty. It's going to be terrible. Okay, so I think I've got pitch, 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 pitch. So I've changed all those. So that looks pretty good. All right. Now what are we ready to do? We have got all of these different terms, so we're ready now to calculate our new signal, our corrected signal, to go to the servos. Okay, we're ready to do that. And so what I'm going to do here is I'm now going to calculate the new roll servo value. And right, this is the thing that we send to the servo, the roll servo. So what is that going to be? Well, it's going to be K1 times the error. And so that would be, well, it's that, but you're adding it to where you already are. So roll servo val is going to be roll servo val plus the correction. Okay, where you were before plus the correction. Well, what's the correction? It's K1 times the error. For us, K1 was K1 and then times, okay, our error here was roll error. Okay, now that is our proportional term. Now we're going to add our derivative term, which is going to be K2 times what? K2 times roll error slope. Okay, it's K2 times the slope plus K3 times the area, which we called roll error area. All right. And now this same thing should be true for pitch. And so I'm going to get this, and I'm going to copy it, and then I'm going to paste it, and then I'm going to come here and I'm going to change this to pitch. So this is our control for our second servo, our pitch servo, and I'm going to copy. I got to make sure I get all of these in here. Change all the rolls to pitch. Okay, that looks good. Now, so I have my new signal for the roll servo. What do I need to do? I need to apply it now. So I'm going to say roll servo dot write. My servo is called roll servo. I'm going to write to it. What am I going to write to it? Roll servo value. Right? That is that corrected term that I just calculated. Okay. Similarly, I need to apply the pitch value to the pitch servo. So I'll copy that and I'll come here. And now I'm going to have my pitch servo. I'm going to write to my pitch servo the pitch value, pitch set servo value. Wow, how many mistakes have I made in this? I don't even want to try to run this thing. You guys are probably screaming and pulling your hair out trying to tell me all the mistakes that I made. So let's make sure, did we do, yeah, we did our time. I'm just going to kind of glance over this. All right. Then we print some stuff out. Let's just go ahead and see if this thing will compile. So I'm going to go ahead and try to run it. Try to download it. Oh, what did we do? Milli new equal millis up here. You guys probably saw I didn't put my semicolon in, so let's fix that. Let's try it again. Okay, probably a similar error. Yeah, roll error old equal rolled error. Okay, that needed one. I think probably down here at pitch I made the same mistake, right? That's what I was saying. I was probably copying and pasting mistakes. You know, I'd code a lot in Python, and Python doesn't use semicolons, and as I go back and forth, I'm always like making mistakes, or I'm putting semicolons in Python where I should. Okay. The DT here, I didn't have a semicolon, and probably down here I didn't have a semicolon, and so now let's try this thing and see what happens. Now I know what that is. When I had my trusty old serial plotter going, I forgot to turn it off, so the USB was tied up, so it couldn't download. All right, it compiled. That's good. Okay, it compiled. That's good. And it's probably going to download. All right, and so let's turn this thing on. So we have P, we have I, we have D. So I'm going to turn this on. Sometimes it takes a little bit to get it to actually come to life. Okay, let's see if this thing is alive. Hey, that is alive. Boom! PID Control. Look at that. PID Control. All right, I've got all three terms. So you can see the thing is self-leveling as I'm moving my arm. As I'm moving my hand, the thing is leveling itself, okay? So that looks good, but you know that looking good doesn't mean that it's doing good. What we really need to do is we need to come back over here, and we need to turn the serial monitor on, and we need to see what's happening here. Okay, so let's say I'm going to roll towards me 45 degrees, so I roll. Okay, we have an instability. Do you see how it's really overshooting kind of badly? Okay. And what that looks like to me is that we have too big of an I term. Okay. We have too big of an integral term, that K3. So I'm going to turn this off. I'm going to come back to the code. And when you have something just overshooting, and I know that my 0.5 is kind of reasonable, and so I think probably I need like another 0 there, because I think that integral term is kicking in and it's causing that instability. And so we're going to have to play with this a little bit to tweak this thing. I might even have to make it smaller. And really the truth is, in this particular case, you really don't need the I term. It doesn't help you, but I'm putting it in there so that you have a real PID controller. Now what you're going to see in this application, it's the work is being done by the P and the D, and we just sort of have the I in there just so you see how to do it, because there will be applications where you need to use I. Okay, so let's turn this thing back on, and let's see if we can get this to come to life. Okay, it is kind of coming to life. I'm going to roll towards me 45 degrees. Oh, wow. Do you see that? Okay, it is still kind of doing that. It's doing it less. This is really working pretty good, but if I put a big tilt, it is still overshooting. So I'll tell you what I'm going to do. So I'm seeing, like, as I move quickly, it is overshooting and ringing. And so what I'm going to do is I'm going to tweak these parameters a little bit more, and I still don't trust that. I'm going to put this as 0.00001, and then I'm going to think about this. What I think is that if it is overshooting as it's coming down, that means that derivative term is not backing off quick enough. That means the derivative term is not really doing its job. And so I'm going to turn that derivative term up. I'm going to turn that derivative term up to like, I'm going to turn it up to 200. because I want it to back off and to pull that thing into a small thing. And also the 200 means that it will respond quicker and then it will back off quicker. And I think that should make this thing more stable. So I've turned I down and I have turned the derivative term up. And so let's make sure that we have this off. Okay, and now let's download this. Turn the power on, and okay, that was kind of crazy, wasn't it? Okay, you can see that this is not happy at all. Yeah, so you can see that that is way too much of the derivative term. I was hoping I could put it up there, but that did not work at all. So we are going to have to go back to 100. Okay, and let's see if we can get it to work at 100. And really, there's not a magic formula. You just got to kind of play around with these things until you get something that looks like it's going to work. And of course, I left the serial plotter going, which I need to turn off. And now let me come here. Let it download. And let's see if this thing will run at a 100 for the derivative term. Okay, we'll turn it on. Need to get it up here where you can see it. Okay, give it a second to come to life. Okay. That kind of is looking pretty good. It's a little jittery. Let's take a look at it on the serial plotter and see what that is really doing. Okay, so I'm going to roll it 45 degrees towards me, and you can see that that is still too much. You see, we get a lot of that ringing that I talked about. What if we just turn D down? I mean, what if we turn proportional down? What if we turn proportional down to 0.25 and let derivative do more of the work? Let's see what happens there. What I hope you guys are doing, and your system will be different because depending on how much momentum, the size of your system, your parameters could be way different than this. Every system is going to be completely different. So now let's turn this on, turn it back on, and then we're going to turn the power on and see what happens. Okay, so I'm going to okay, this is kind of interesting. I'm going to roll towards you 45 degrees. Okay, you see that glitch on the way down. Now that derivative term is so large that it's almost preventing it. The derivative term is so large that it is actually slowing the system down because it's coming in too slowly. Remember, the derivative term works against the proportional term on the way down, and so now derivative is too large and proportional is too small, but there is an aspect of this thing really tracking well until I do a fast change like that. Okay, so I think that that derivative term is a little bit too large and the proportional term is a little bit too small. So I'm going to go to 0.4, and then I'm going to go to about 80. All right, and let's use that. No good. Turn the serial monitor off. Call up our code. Download our code. Okay. We will come back to the serial plotter. I think this is going to work, guys. I think this is going to be a pretty good value here. All right. We will open that, and we're going to turn this on. Okay, it's come to life. I'm going to roll 45 degrees towards me. Oh, look at that. Okay. And I am moving this thing fast. And do you see how it is responding quickly? I'm going to pitch. I'm going to pitch. Okay, still on the way down, it's almost like that derivative term is still too large. And the reason I say that is you see you're coming down and then it just almost stops right here. That derivative term is bringing it in nice and smooth, but it's actually slowing it up at this point. So that derivative term, I think I'm going to make it 70. And then I think I'm going to make this a little bit bigger of about 0.5. And let's try and see what happens there. And guys, this will probably be the one that I'm going to use. And let's see here. It's going to download. Okay, come over here, open this up. And then we are going to turn this on. Okay. Okay. So now I'm going to roll. Okay, so now I will roll towards me 45 degrees. Okay. Roll towards me 45 degrees. Pitch. Pitch. Okay, guys, I am really thinking these are pretty good parameters here. Do you see as I'm moving? It's really, just sort of visibly now looking at the platform, it is really keeping it really pretty nice. Okay, I'm going to roll towards me 45 degrees. Okay, getting a little instability there. Okay, as much as I hate to, I'm going to have to turn the derivative down. Okay, that is still too much derivative. I'm going to make it like 55, because once it starts going like that, that is that fast responding derivative term, and it is just too much there. Okay, turn my monitor off, download the code. Okay, we'll turn this back on, and then we will turn the system on. Okay, it's come to life. Okay. All right, so I'm going to roll towards me, roll towards you, then I'm going to pitch. I'm going to pitch the other way. Okay, look at that. Now practically this is really working very well. Now I'm going to try a quick roll 45 degrees towards me. Look at that, it came in very nice. A quick 45 degree roll towards you. It's coming in very nicely. Pitch. Okay, and you see, look at that, that pitch is not overshooting now. And you see it's operating very quickly. Like if I do a 45 degree pitch, do you see how it didn't go off the screen? It never got to an error of above 20. So you can see the derivative term coming in and really correcting it, rolling. Okay, so guys, as I look at this, for me and my system, it seems like kind of the best parameters were 0.5 on the proportionality constant and 55 on the derivative term, and then this 0.00001 on the integral term. That's just almost turning the integral term off because it's really not needed. But what I really want to hear is I want to hear how this worked for you. I want you to tell me what I guess this is your homework. What were your K1 and K2 values that you used that got the best performance out of this thing? And it's like, it's really kind of hard because maybe as you make K1 bigger, you've got to make K2 bigger, but then you reach the point that there's just not stability. And then if you bring them down, if you're not careful, you're just not getting the performance out of the system that you want. And so the goal is to have it as quick as possible and as stable as you can. And what values did you find? And put your values in before you read other people's comments. For me, it seems like 0.5 and 55 is sort of the sweet spot as far as getting this thing to go. So man, PID Control, it's basically solving calculus problems in real time on the Arduino. You're finding the derivative of your error curve, you're finding the integral of your error curve, and you're creating a correction signal that has three parts. Part of it is proportional to the error, part of it is proportional to the derivative of the error, and part of it is proportional to the integral of the error. And I hope that even through this video you could see that with those three components it works much better than either the constant correction or the proportional correction alone. Okay guys, this has been a long video, a little bit tedious, but I hope some of you made it through. If you made it through, you know, give me a comment letting me know that you watched the whole lesson. If you like the lesson, think about giving us a thumbs up. Subscribe to the channel. When you subscribe, make sure to ring the bell so that you get notifications on future videos. Appreciate you guys tuning in. Would really like to hear your feedback down below. Paul McWhorter from TopTechBoy.com. I will talk to you guys later.